Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field.
This show is brought to you by Automotive Seminars. If you're looking to stay up on the cutting edge diagnostic strategies and techniques, this is the place. You've got live 4-hour seminars that are put online that you can join in, ask questions, interact with the instructors with some of the best of the best. They've got Keith Perkins and John Thornton putting on classes like network diagnostics, mechanical engine testing, advanced electrical testing, and GDI diagnostics, and a ton more. And once you purchase one of these training seminars, you can access this at any time that you want through your account at automotiveseminars.com. You can rewatch the training a year, 2 years later, which makes this training even more valuable. So I highly recommend you check this out. The link is in the show notes. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping. I will be your host once again for this week's show. Thank you so much for joining me. You got just me this week. We're going to talk about CAN bus. And you're probably like, geez, Sean, you've talked about CAN bus before on this show plenty of times. Communication issues and diagnosing things that are wrong with vehicle networks. And you are correct. I definitely have this as a recurring theme on the show. But why do I have it? Because it is a consistent, prevalent issue that we get called out for, meaning that it is either a subject that technicians and shops do not want to address. Maybe there's some hesitancy or fear behind getting involved, or just a lack of skills and knowledge. And maybe part of it is that it's challenging in a way, but I really don't think so. I think there's a lot of other more challenging diagnostics out there, to be totally honest, because there's some pieces of knowledge, some tooling, and some understanding about the system that actually make it relatively simple to get to the conclusion, right? It's like if you understand the rules of the game, it becomes a lot easier to play versus if you don't understand the rules of the game, good luck. That's kind of what it is for CAN bus. But anyways, I'm talking about it again because a lot of the case studies and the things that I bring up on this show are just mirrored off of what we are seeing out in the field and what we are getting called out on most. And then on top of that, it's something I feel like I can offer some useful knowledge on because we're successful with this style of diagnostic. So I'll go through some pieces of information that you may already know. Maybe some of them you don't. Maybe some of them are good refreshers, but it is stuff about CAN bus that will help you get to the problem faster. And then I'll talk about a car or two as well that we've seen recently. So obviously, if you're going to get into a network, if you feel like there's a network problem, you're going to want a diagram and topology of the network. You want to understand how the network is constructed on that car. And I've talked about that plenty of times before, right? Is there a gateway? Is it a daisy chain style like a GM and other manufacturers do use that as well? Or is it the traditional bus style? Where are the terminating resistors located? Sometimes that's in a diagram. Sometimes that's in a separate topology map, which isn't a traditional wiring diagram. It's just a layout of, hey, here's all the modules that exist on each bus, and then you see where the terminating resistors are. Sometimes it's in service information. Sometimes it's the description and operation. What I would suggest, if you're looking at a diagram, you don't see the terminating resistors for one reason or another, if you're using service information that has a search bar, which I think all of them do, but we use all data and Identifix, just search terminating resistor. And a lot of the times it will jump you to the piece of service information that has where they're located. And again, that might be in a description operation, not as intuitive to find it. But again, important to know where those are, because if you decide that you're going to ohm check it based on what you're finding with the network, again, you want to know where those are located, because it will help you significantly to determine maybe where the open is, or potentially where your problem is in the network. Now, if you're going to ohm check the network, you want to find that 60 ohms, right? The two 120s in parallel. Do that while there is no voltage on the network. It's really important. And I've even forgot this sometimes, that your ohm meter that you're using to measure that resistance is going to be affected by voltage on the network, because it's using voltage to determine the resistance of the circuit. If there's extra voltage, especially fluctuating voltage, you're going to get wild readings, or just plain incorrect readings of the network. So you want to make sure there's no voltage. So if I'm using a multimeter, what I do for this is I'll just put it on my DC voltage setting first, and I will go across the two CAN lines. You can go ground to the CAN lines, but I'll just go across the CAN lines, and I want to see 0, right? If there is a difference in voltage between the two CAN lines, right, there's message or data being transferred there, you'll see it there. You can do it with a scope too, but that's just the way that I'll make a quick check. And if I see, okay, there's no voltage there, I will go to my ohm meter and then measure the resistance. If you want to be really sure, just disconnect the battery, right? There's not going to be any data transmission or bias voltage or anything on the CAN lines if you disconnect the battery, right? And I might be jumping ahead a little bit here, but if I determined that there is an open and I want to ohm check to verify, then a lot of my diagnosis with an open can can be done with a disconnected battery and just an ohm meter. So then I don't even need to connect the battery back up. I'm just going to go at it that way. Now, how could I determine that there's an open network prior to even ohm checking it? Okay, well, again, that depends on the construction of the network, right? It's going to change things if I'm working on a GM versus a Ford. But looking at the modules I can talk to in relationship to the topology map kind of gives me like maybe a clue, like, hey, I can talk to this module, this module, this module, and nothing else. Here's my DLC. Here's how the network's constructed. Here's where these modules are located in reference to where I connect with my scan tool, right? So let's say I'm hardwired into a medium speed bus on a Ford F-150, okay? That means I'm connected with the scan tool there. I'm talking on the medium speed bus. And there are two modules that I can talk to and nothing else on that medium speed bus. And I look at the topology of the network diagram, and I see that here's DLC. Oh, here's a module that I can talk to. Here's a module that can talk to. And they're the first in line, like physically in line to the DLC. It goes wire out of the DLC and then out to module A, then module B. And then after that, there's other modules, but I can't talk to any of them. That's a big clue to me, like, hey, I might have an open. Okay, now if I can't talk to anybody, different story. Still could be an open, but I might consider something else. But if I can talk to module A, B, nothing else, I'm thinking open, right? I'm reaching for that ohm meter pretty quickly there to check to see is what I'm seeing correct. Same thing on a GM and a GM with the daisy chain style. Even more so, I can talk to module A, B, C, nothing after. Okay, there's a good chance there's an open between here and here. And the nice part is with this too, this line of thinking, looking at the topology, using the scan tool to see who I can and can't talk to, I can already start to get an idea of what leg of the network, what like section of wiring I should be looking at, looking at connectors and splice locations based off of who I can talk to and who I can't, right? It's just getting my mind going for the actual diagnostic, and I haven't even left the driver's seat, okay? And so the next thing that I'll do, I'll probably scope the network. I could ohm check here if I decide to because it's an easy check, but I use my U-scope a lot. And let me tell you, for CAN bus diagnostics, and this includes single wire LIN bus stuff, but we're really talking about CAN here. The U-scope, or something like it, a little handheld scope, is all that I need for 99% of my CAN bus network diagnostic stuff, right? I have a Pico. I really like it. I do pull it out sometimes for CAN bus, but not that often. Now, is there some really cool, like nitty gritty stuff that you can get into using a Pico? Yeah. Can you see way more detail and analyze it in a whole nother fashion with a Pico? Yeah. Can you look at multiple channels at once and use math channels? Yeah. Can you use the serial decoder? Yeah. That's all really cool stuff. And I think it's worthwhile. But that being said, most of my CAN bus diagnostics happens with a single channel U-scope. And what that piece of that I really want to transfer to you is that problems with CAN that can be seen on a scope, or information that clues you into the problem of the network via a scope, is usually very obvious, right? Yeah, can you pick out the little nitty gritty stuff and maybe that's your issue? Sure. Adam Robertson and Gary, I forget his last name. They have a CAN bus network class that's phenomenal, and it really gets into the nitty gritty stuff and serial decoding and XY access. And take the class; it's so worth it. And maybe even me taking classes like that over the years has helped me get to the point where I can diagnose it with a U-scope. But I'm going back to this, and I'm sticking to it. Is that most of the problems that we see are very obvious, and they will show up on a single channel U-scope where you don't even really need to zoom in that far. No, I'm not saying you never do, right? You very well could need that Pico. And if you have it set up and ready on a cart, why not, right? The multi-channel makes it real handy. You can check multiple places in the network at one time, compare them against each other. You could look at, multiple networks at one time. There's definitely a reason for it. But again, where I'm going with this is most of the problems that you see with the network are going to be very obvious, right? If you've got an open in the network, if you've got a corrupted module, if you've got a module that is missing a power or ground, things like this you can pick up with that U-scope real easy. So back to, let's say, an open network, right? We see on the scan tool, okay, I can talk to a couple modules. Maybe now I'll pop a scope on there. Now, you do need to access to the network. Depends on the car how you're going to do that. But get to your network and tie into it. Just understand if you have a gateway module of some sort, you're going to have to get on that network somewhere. And maybe that's easier said than done depending on the application. But you're going to want to do that. Now, you're going to scope it, and we're going to look for the basics, right? It's that 2.5 on high, 2.5 on low. The high side is going to go to 3.5 during data transmission. The low side is going to go to 1.5 during data transmission. They should move at the same time, right? When high goes up, low goes down at the same time, should mirror each other. You might say, well, how can I see this with a single channel scope? What I do with my U-scope when I'm looking at a CAN line with a high and the low side is I'll look at each side individually, right? So I'll have my scope grounded. I'll look at high, I'll look at low. Okay, that looks okay. That looks okay. Maybe one doesn't, right? Maybe one looks like it doesn't belong, but if everything's good, I should see that. And then what I'll do is I will go across CAN high and low with my single channel. And that's going to change your voltage level of the data packet, and it'll actually start down at 0 for your scope, but it will make a very nice clean square wave. And I do that sometimes to eliminate noise in the system. It's surprising the amount of noise or what you might think is garbage on a CAN bus that can be present, and data transmission can still happen. I've been surprised at what communication could happen with modules when the network looks like garbage. Heck, I've even programmed modules on a network that looks like trash because, like, we get called in like, hey, we replaced this module. Can you program it for us? Sure. And we program it, and then after the fact, we're looking at it and we're like, hey, this thing's got all kinds of communication codes in here. It did before too on the pre-scan, but we're like, you still got issues here. Then we end up scoping the network, and it's just trash from a corrupted module or something. And I'm like, how in the world did I program something on this network? Or how did I communicate with anything on this network with it, looking the way that it did? Well, number one, CAN bus is robust, and they say that in the name. And it is surprising, but it's using the differential method to determine the data packets. It's looking at high versus low. And when you look at high versus low, you see what the computer or the modules are seeing, and it clears things up a bit. It gets rid of some of the noise. Now, I say that, but I think it still is important to look at each side. Now, if you're using a 2-channel scope like a Pico, okay, put channel A on high, put channel B on low. You have got the the high and the low, you got those stacked on top of each other so you can see them, and then add a math channel, right? You do A minus B or B minus A, whichever one that you got to do, and then you should see a square wave that's generated that actually looks like a usable data packet. And, the GMs with the wavy CAN signature that looks like there's a problem, but then you go across and there's not. I like to look at it both ways and then kind of make a determination. Now, if I've done this and I'm suspecting an open, depending on how the network is open, where it is open, and where you're testing, you might see a few different things. But I'm going to give you one example of a very common waveform that you might see on a traditional bus style CAN that has an open somewhere. If you look at your bias voltage, which should be 2.5, right? Resting, no transmission, the flat part of the waveform, you got 2.5 volts. If you see at times it go high to 3.5 and you see it go low to 1.5 on the same side of the network, right? I'm just looking at CAN high. It should always go high, but it goes low. And when it goes low on the high side, it sometimes is lined up with data packets and sometimes not. What this is indicating, if you see this is an open network. Well, it's either that or somebody crossed wires to a module, right? They went high to low and low to high. That's possible. I've seen that. Less likely, but it's possible. That's going to be something that you can determine with ohm check, which would be my next step. But most of the time when I see this, the CAN waveform going high and low on one side of the network, that is an open. And my best way to explain this is that the voltage from the intact side is affecting the voltage on the open side through the terminating connector that is still connected, right? So unless you have a complete open, and that's going to give you a different waveform here than just one side open. I probably should mention that. That is important. If you're seeing this, it means that there's an open on one side of the network, not both, but that voltage can actually bleed through the terminating resistor that is still connected, and you're seeing it on the opposite side. Now, I may not be explaining that perfectly technically correct. And in all honesty, I'm still trying to understand the technical side of it. But what I can tell you from real life, from doing a lot of CAN diagnostics, when you have an open just on one side of the network, you still got a terminating resistor connected, you will see that voltage go high and low on the same side of the network in reference to the bias voltage. So it's a good clue, right? So again, going back to the initial diagnostic, if I can access the bus that I'm trying to from the driver's seat, which you often can through the DLC, you can see this, and now you've got two confirmations that you have an open CAN network. Now you can do your ohm check with the key off or the battery disconnected, and then for sure confirm it, and then break down the network from there, right? If you know where the terminating resistors are, and you know the modules you can talk to, and you know the construction of the network, you're going to get there pretty quickly, okay? Then you're just using connectors, splice locations, things like that, and you can narrow down the section of wiring fairly quick. Hey, have you ever been faced with the challenge of sourcing, installing, and programming a used control module in a vehicle? I know a lot of us have. it seems to be happening more and more often today with the volume of control modules on vehicles, the cost of some new ones, or even the availability of new control modules. In some cases, used may be the only option. So what do you do here? I strongly recommend checking out SJ Auto Solutions and Tommy Oliva. Tommy offers a cloning service for used control modules to make these things plug and play for the vehicle that you're working on. In a lot of cases, he is also able to source the control modules if you're unable to locate one for the vehicle that you're working on. But once you get connected with Tommy, he's going to offer fantastic support from start to finish to make sure that that control module is going to work in your application. He's also got tech support that he offers through his website, along with some free resources there as well on information about used control module programming. So make sure to check out SJ Auto Solutions. I can't recommend that enough. Right. Now, the other waveform that you might see if you have a complete open where the section of the network that you're connected to isn't connected to any terminating resistor, you're going to see a different waveform. And this is going to be kind of a ringing pattern. It will be repeating peaks with almost no break. There'll be no data packets. It's just an up and down waveform with repeating peaks and a smooth curved transition at the bottom, right? Where you would see the bias voltage be flat. It's a curved waveform to go back up to the peak, right? So it's like a repeating, very narrow mountain peak, almost like a compression tower in a compression waveform. If you're familiar with looking at in-cylinder waveforms, what your compression tower should look like with a nice curved ramp up and then curved ramp down. You almost see that in the CAN waveform. This is a completely open network, right? No terminating resistors, but there's still a module or modules on that leg of the network. You can see that. Now, caveat here, I did see one the other day that looked very similar to this. I thought it was open, but I used my ohm meter to verify. Turns out it wasn't. It was 60 ohms, and this was just a module that was corrupted, causing this waveform. So it's not always, these things are not 100%. You'll find differences in different cars and different networks will change things up on you a little bit, and that's why I use multiple things to confirm what I'm thinking. Okay, I will use my ohm check. I will use the modules I can talk to in reference to the style of network. I will use the scope pattern. And if all those point to, hey, I have an open, okay, well, let's go find it. In this case, it didn't. My initial thought when I scanned the network, now a clue here on this car, this is a Buick Enclave, I couldn't talk to anything. And then when I scoped it, my first thought was, oh, this is an open. It looks like that ringing, repeating network that I mentioned, but then I ohm checked it and it was 60. And I'm like, okay, well, there's not an open. And then I just had to break the network down, right? If you have a whole network down, divide it into sections. Find a place to separate it somewhere, somehow. And unfortunately, on some cars, that's not so easy, right? A connector or a module is often the place to do it. Some networks just don't give you the ability to separate them. I've been in that situation. So then you have to make the decision. Do I want to depin a connector? That's a possibility. Sometimes that's not even a question. So then you have to weigh the decision of, do I want to cut the network somewhere and then repair it? And I've done that, and I will do that if that's the way that I need to get to the solution, right? I'll fix the wire. I'll probably determine, like, if this is underneath running next to the transmission near the exhaust or something, I'm not going to be cutting those wires open unless I absolutely have to. But if it's behind the glove box, a point where it's not going to be exposed to the elements and road salt and all that stuff, sure, we'll cut it, we'll fix it. And I weigh in my mind, does the time to repair this wire that I'm cutting benefit me enough to solve where the problem is in the network, right? If dividing this network here saves me 45 minutes of accessing and unplugging single modules one at a time, I will do that, right? It's faster to fix a couple wires than to access 5 modules and that are behind panels with bolts and screws and all of this stuff. So I'll weigh my options there, and I may cut a wire, and then obviously you got to repair it properly. The other thing that you should consider, and this is definitely important depending on the scenario of what you have, is if you're separating a network and you're disconnecting a big connector, you could be cutting power or ground to a module that is causing your problem, right? So you've got a module that's corrupting a network, and you remove power to that module. Well, it stops corrupting the network, but you disconnect this big connector, which removes power to said module. That's the same thing as unplugging the module. So that's where it can get tricky. So you may want to depin the connector if it's a real big one and it's got a ton of wires on it. That might be worthwhile, right? Because that's the only way to divide up that network into sections to find where the issue is. Now, another thing that you want to look at when you're looking at the CAN bus waveform on a scope, and again, you can do this with the U-scope, is pay attention to the bias voltage, but look specifically at what the voltage level is. Okay, now on a regular high-speed CAN bus, should be 2.5 volts when there's no data transmission. But if that voltage level at the bias is significantly elevated or below 2.5, that can possibly clue you into the problem that you have. It's not 100% across the board, but I've found it to be pretty accurate to finding specific problems with a network. Now, what do I mean by this? If the bias voltage is elevated above 2.5, right, when there's no data transmission happening, but you're still above 2.5 volts, it's very possible that a module that is connected to the network is missing a ground or has a poor ground. Okay, so a poor ground to a module can cause elevated bias voltage level. Same thing's true for the power, except for it's in the opposite direction. A missing power feed to a module that is on a network can cause the voltage level, the bias, to drop. Now, there are a ton of nuances to me saying this, so you shouldn't take this as the gospel of CAN. I found it to be pretty useful, but there's so many different variables here that come into play that you want to use this as a consideration and not a tool for a final diagnosis. You probably really couldn't use it as a final diagnosis, but you don't want to say for sure, hey, I've got a module with a bad ground, but you might. But how many grounds does that module have, right? If the module only has one ground and we remove it, it may not affect that CAN bus at all. But if it has a couple grounds, or again, maybe if the ground is just compromised, it's not completely out. Same thing with a power feed. And the power feeds where it gets real tricky because a module can have 3-4 different power feeds. And what does cutting this one power feed do to the module in reference to the CAN bus? It might still communicate just fine. It might communicate fine, but do some weird stuff. It might affect the network and move that bias voltage. What I'm saying is just to pay attention, okay? Because often when we're at this point, we have a lack of communication. Maybe we have a corrupted bus. We see it. We know what a good CAN waveform looks like, but what we're seeing on the waveform looks like just crap. It looks like garbage, right? You do the across the two sides, and it looks nothing like a usable square wave. And at that point, I'm going to be looking at that bias voltage just to see what it is, because if it's elevated, if it's reduced off of that 2.5, here's my thought that I need to keep in mind as I pursue what's causing it, right? Because we still got to break it down. We still got to find the source. It's probably going to be a module here, most likely, or modules. But when I get to said module, as it really should always be, but this is just a helpful reminder of like, I need to verify that the grounds or powers are good to said module. Okay, and I've run into this plenty of times where I had an ABS module on Acadia, caused the whole network to be down, a garbage waveform that looked like, completely unusable, and it was because I couldn't talk to anything, but the bias voltage was up at like 4 volts. It turned out it was a loose ground underneath the airbox on that one. Ford F-150, I've had this happen a couple times. We have communication issues on the bus. The bias voltage is lower, and it turns out there was a power feed missing to several modules, so several modules on the bus. And the reason that this happens is that every module contributes to the bias voltage on the CAN, right? Every node on the network, every module that talks on the CAN contributes to the bias voltage that is present. And so if you have the ground or the power affected, compromised in some way to a module, it is also going to affect that bias voltage in most cases. Now, what's the extent of it? How can you interpret it just from the waveform to what's wrong with the car? Again, I don't think that single data point is enough to make a call, but it's going to grab my attention. All right. I am going to at least observe what is my bias voltage when there's no data transmission. And if it's 2.5, okay, cool. That's what I want to see. I'll look at the rest of it. I'll see, what else I got going on. But if it's elevated or it's reduced, I'm still going to continue on with my normal process to find out the source of the problem. But when I get there, power or ground is top of mind. I got to make sure that, I'm using a headlight bulb or whatever's necessary to verify that I have, proper current flow to that module. And also that I'm not missing any powers or grounds to said module. Also really important there. Now, the other thing that you might see is a completely elevated voltage either all the time or during data transmission, right? So what I mean by that is you look at the CAN bus and it's 12 volts or it's battery voltage all the time. Clearly a problem, clearly a short to power. Or maybe it's only when the data transmission happens, right? Maybe it comes all the way up to battery voltage during that point. Now, I can't say that I've seen a ground cause that. Maybe it can, but in this case, it's usually a module that is shorted to power internally, right? There's some corrosion on the board or something wrong on the board that's causing power to be, fed onto the CAN bus, like straight up battery voltage. Clearly a problem. In this case, we're going to be breaking this down into different sections of the network as well. But in this case, you do have the option, depending on the setup, of removing power to modules that are on the network via a fuse. Now, one thing you can also look at here is cycle the ignition while you're scoping it. And if that voltage drops back down to a regular level on that CAN, right, you'll still have CAN communication immediately after you shut off the key for a period of time. And if you see that, like, voltage come all the way down, I mean, at least at that point, okay, this is at least an ignition fed power that's going onto the bus, and can I look at a power distribution schematic and maybe break this down using a handful of fuses to say, well, it's definitely this ignition feed, which modules get it from this, and break it down that way. This all depends on the construction of the car, right? I'm trying to figure out a logical, efficient testing path depending on the vehicle and the topology that I have. Is it not easy to break this into sections? Okay, then let's see how we can break it down via module and power feeds. Okay, it's all going to change depending on the vehicle that I'm working on, looking at wiring diagrams, understanding location of components. And that's the trouble that you run into a lot of times is there's 20 modules on here and 10 of them are just an absolute bear to even access. So we need a better way of, narrowing down who's causing a full 12 volts on this bus. So, like I said, we can look at is the switch power feed or not. We can start pulling fuses to modules. This does get tricky, though, because there's a lot of modules that have multiple power feeds. And there's a lot of fuses that feed multiple modules. So that part of it gets tricky. My favorite still is dividing the network via a connector. Again, not always possible. Do I cut somewhere? I weigh that risk. Bringing this into a car that I had recently, I thought this one was pretty interesting. It was a 17 Lincoln MKC, like an SUV. This was a flood car that had actually been repaired somewhat by another shop, and then this went to another shop. And what they had done, and I didn't know this going into it. I knew it was like an auction car. I knew it had been a flood car, and it actually ran and drove. But we found that the high-speed toucan was completely down, shorted to power, and because of that, we could only talk with, I think, the high-speed can 1, but there was also high-speed can 3 and medium speed. But on this Ford, the gateway module, when it's the OBD2 plug, and when you plug in, you're hardwired to high-speed 2 and 1. Now, you could talk to everything on high-speed 1. You couldn't talk to anything on 2, 3, or medium speed, but 3 and medium speed get transferred through the gateway module onto high-speed 2. All right, so I know it gets a little confusing, but high-speed 2 is how your scan tool talks to the gateway. And then the gateway translates messages from high-speed 3 and medium speed. So if something compromises high-speed 2 or your gateway module, you're not talking to those other two networks. Now, you can access them from the plug on the back, which I did. 3 and medium speed were fine. High-speed 1 was fine. High-speed 2 shorted to voltage. So that's the summary. That's the bad part of the car. Okay, let's find it. And we were using connectors, and we ran into some of the problems where when we disconnected the big connectors with lots of wires, we were cutting power feeds to things that were causing the network to come back down to its regular voltage level. Now, one thing you can do here is use your scope, and as you're disconnecting connectors, look at both sides. And that's what I'll do to try to track down, well, what side of the network has my problem, right? I'm separating it in one place, and I'm looking at this side, I'm looking at that side. Well, which one has 12 volts? I'm going to follow that side. Pay attention on your wiring diagrams here. This is helpful. Your wiring diagrams will show a little arrow that is going to point in one direction and a line coming in through the backside, right? This is male, female, and I think you can figure out how that works, but you can look at the connector and it matches the diagram. And so that way you can look at your connector, you can say, okay, well, the female side has the 12 volts. You can look at your diagram and say, oh, there's the little arrow. Oh, okay, I got to go this way on the diagram. So physically looking at the connector and then physically looking at the diagram, and then seeing what you have on your scope after you separated it, now you have a direction to go to. But what if I disconnect a big connector, right? I had 12 volts short of this network. Now I scope one side, I scope the other side, and now they're both good. Well, disconnecting that big connector may have cut power to the thing that was shorting voltage to the bus. That's where we run into problems separating large 20 plus pin connectors. I mean, it could even be on an 8-pin connector. You'd have to go through every single pin on that connector and see, well, what does this go to? And that's more work than I want to do. At that point, I will decide, do I depin this connector? Maybe. Is that easy enough to do? Sometimes not. Or do I cut this wire? Because it's in a location where I can repair it easily once I'm done, and it's going to save me enough time that repairing the wire after is less time that I would have spent unplugging modules one at a time. Hopefully that makes sense. Now, on this one, I'm glad that I did cut wires on this one, to be honest, and I'm glad I did, because I could have unplugged every single module on this network. And I did have it down to a certain section, but there were still several modules, and I could have unplugged every single one of them, and it would have maintained the 12 volts present on there. And here's why. When they did repairs to this thing after the flood car, there are several splice packs underneath the carpet. And one of these splice packs, well, it's really just a bunch of twisted wires soldered together with a piece of tape over it or a heat shrink over it. One of these is for the high-speed toucan. It's a green-orange wire, so it's a green wire with an orange tracer. And there's several wires that go into this splice underneath the passenger side carpet. So we're tracking this down, trying to figure out where this 12 volts is coming from. And we get to this splice because it's the next thing for me to test, or it's the next, stopping point that I can locate within the network based off the diagram. And we look at it, and there is a bunch of green-orange wires going into it, but there's also a green wire of the same green, but there's no orange tracer. And it sticks out because it's also a larger wire, right? The gauge is different than the CAN wires. And that seemed odd. And I'm like, And I looked at the diagram, and there's no green wires anywhere on the high-speed 2 CAN. It's on that side, it's all green-orange. I'm like, that's strange. Let's cut this out of here and see what happens. So I cut it out, and we get the whole network back, and I have 12 volts on there. I'm like, okay, so somebody tied in the wrong wire. And I'm looking through the harness close to where this wire is located, and I find another splice pack with a bunch of green wires of the same size with no tracer. And we actually looked at the power distribution diagrams, a little bit of deducing based on who we could talk to, who we couldn't. And this was a power feed for the side detection modules and a couple other things. But that was a splice for power. Somebody had taken the wire, put it into the wrong splice when they repaired this thing. And that's a tough one to find, right? That's a man-made problem. We're probably never going to see that ever again. That's a one-time thing. Maybe, I don't know. Who knows? Maybe somebody else probably do something similar. We'll definitely see more man-made problems, but maybe not that one exactly. And that's a tough one to find. Again, because you could unplug every single module on that thing and you'd still have the 12 volts on there. Instead, what I tried to do was break down that network into sections, and I was using connectors until I couldn't, and then I was cutting wires and then repairing them once I was done. So again, different ways to approach it. I just wanted to give everybody some tips and clues, information when you're getting into these CAN diagnostics. You can find the problem. It's not too bad. And you don't even need a bunch of crazy tools to do this with, right? You need an ohm meter, a single channel scope, and a test light, and you can solve most of these. A scan tool. Scan tool helps a lot too. But anyways, that's where I'm going to leave this one today. I want to thank everybody for listening and all the support for the show. I really appreciate it. We'll have an interview up here next week. Tommy will be back. But in the meantime, let's all get out there, start fixing the world one car at a time.
Thank you.